Hello everyone, I am calc and welcome to my first video in almost 2 months actually. Maybe just around 2 months, maybe over, I didn't check. Anyways, I wanted to start off the year by talking about something really interesting to me. The following problem. Can you come up with a function that goes from the real numbers to the real numbers? It doesn't have to reach all the real numbers, you know how functions work. But it can come up with such a function where it is continuous on all the integers and discontinuous or not continuous everywhere else. Now, some of you might be wondering, what the heck does continuous mean? What are we talking about here? Well, continuity generally gets described as when we go from one value to the next x without any gaps or jumps, but that's really vague and inconsistent and doesn't really make much sense. So let's talk about continuity in terms of a very simple function, just y equals x. So when we say there are no gaps or jumps, we mean that whenever I'm really close to any value, let's say this is x equals 2. Whenever I'm really close to x equals 2, then when I plug in the function, I'm going to be really close to y equals 2. And this works in both directions. So no matter what, I'm going to be within a certain distance. Now, the way we define this mathematically, the way we make this a little more rigorous per se, is we say that if we want to be within a certain value of whatever our y value is, let's say 2 like before, if we want to be within a certain positive value, epsilon of 2 in our y value, then we just have to get within a certain distance, delta of 2 with our x value. So if we want to get close with the y value, we just have to get close enough with the x value. It's a law of approximates and inequalities and stuff, but it works pretty well. Now, if I want to be within, let's say, 0.1 of this, I just have to be within 0.1 of x. And you can do it with other stuff too, like let's say y is x squared instead, and we want it to be within 0.1 of, I don't know, 4, for example. I may have just chosen a hard one, but it doesn't really matter. I don't know. The point is you can find a value here such that when you're within this much, when you're that close to 2 with your x value, you're going to be within 0.1 of 4 with your y value. So now we've established what continuity is. We think back to most of our functions, we can think of points where it's not continuous. 1 over x certainly comes to mind. Can't be continuous at infinity, because you're always going to be way far away from whatever the heck is that value is, positive infinity, negative infinity, point at infinity, whatever. No matter what, you can't get close to it, so it's not continuous there. So we know of functions that, have 1 or 2 points. But what does it mean to be discontinuous at an infinite number of points? Well, to introduce that, let's talk about a function that is discontinuous at an infinite number at every point. Now, some of you are going to look at this and say, well, I'm just being stupid. This doesn't pass the vertical line test. Therefore, it's not a function. However, this is just because the drawing doesn't really capture a function. The problem is, though, the drawing can never capture a function, because over here where the values are 0 is the rationals, and where the values are 1 is the irrationals. So, okay, this obviously passes the vertical line test now, but why is it discontinuous? I mean, I can get close here, for example. What's to stop me from getting close, like, here? Well, truth be told, not too much. If I approach with any rational here, like, let's just say 1. So 1 is going to value 0. And if I approach with the rationals, so I start with 3 halves, 5/4, I don't know, 9/8, and I keep going with that. Each one of these has a value of 0. So, no matter what that I do, I'm within a value of 0. Well, from where I want to be. So it looks like we're done, right? This is continuous. Not so fast. Consider the following sequence. Root 5 over 2, or 2 squared plus 1. Root 10 over 3, 3 squared plus 1. Root 17 over 4, 4 squared plus 1. Root 26 over 5, 5 squared plus 1. You see where this is going. This is going to get closer and closer to 1 as we go along. Like, even just the tops are getting closer and closer to the bottoms, just arithmetically, without even the dividing. But every single one of these is irrational. You can check that for yourself if you want to do, like, that proof. It's kind of fun. It's similar to the root 2 proof, if you know that one, but, you know, it can be fun. So, all these are 1. And as we keep going, we're going to keep getting irrational, so it's going to keep being 1. And no matter how close we get to Q, and we're going to get really darn close as we want, actually, we're never going to get close to 0. So, over all the rationals, it must be discontinuous. And you can say the same thing about the irrationals. So, okay, you're thinking. So this is nowhere continuous. We have stuff that's continuous everywhere but a certain amount of points, finite number of points. And we've seen those. We can make those if we want to. We have functions that are continuous nowhere, but a function that's continuous on an infinite number of points and discontinuous on an infinite number of points? Preposterous, you might think. Well, you'd be wrong. So, let's start trying to create this function. If we reflect the idea with the 1s and 0s, maybe we can capture it a different way. So, let's say I move the function from before down a bit. So this is at -1/2. This is at +1/2. Still irrational, still rational. Not to scale, obviously, because I never draw anything to scale. But now, these values are always going, now we see it, these values are negative and these values are positive, so they're always going to have to be a certain distance apart, and we can't get as close as we want with them. So let's keep it this way. For our function, which remember has to be continuous on the integers, and we'll get to that, we want this to be positive, to be greater than 0 on the irrationals, less than 0 on the rationals. But so far it's still discontinuous on the integers, just like everywhere else. But consider this. What if, since we have positives here and negatives here, we have them approach the one thing they can't approach, 0. So, here when it's not an integer, I'm going to draw this a little bigger to be clear. So, rational numbers that aren't integers are negative, the irrational numbers are positive, and the integers are 0. And reflecting our idea of continuity from before, a really basic one of getting close, of when we get close with x, you want to get close with y. How about the closer you are to an integer, the smaller the absolute value of the function is? So what does that look like? Well, if we start with the irrationals, it has to be really close to 0. Basically 0 when it's basically at 0. Then it goes up, goes back down, and it's going to be -1. back up, back down, -2. Does the same thing on the other side too. 1, 2, so on and so forth. And for the rational numbers that aren't integers, we can do the same thing except negative. So we have this here, and this, and here, and this, here, this, here. So, obviously, when we get close to the integers, everything's basically 0. So it's continuous there. What about everywhere else, though? What happens when you have a rational number really close to the integers? Well, if we approach from the irrational numbers before, let's say our function is negative, I don't know, c. So our rational number, you plug in the function, it's negative c. As you get closer and closer to with the irrational numbers, just because it's symmetrical, we say that, let's say we have an I really close to q. So I is approximately equal to q, but it's irrational. Then it's going to be approximately equal to positive c. And so when we get close, the difference is always going to be within a certain distance of plus 2c instead of 0. And it's going to not get, so there will be a certain point where you're trying to get closer and closer to 0, and it's just going to be impossible. Just because how the function works. For example, you could select you want to be closer and closer to this, actually. My mistake. But if you just say it has to be within c over 2, then the maximum possible value is negative c over 2, while the irrationals are positive, so they can't get that close. So obviously it's discontinuous on the rationals, and you can do the same thing with the irrationals. So, with that established, and I hope you enjoyed that, here's a question for you. Can you come up with a function that does the opposite, where it's continuous everywhere except the integers? It's not too hard, actually, when you work on it for a bit. So I'll leave you with a few more problems. I'm not going to ask you to find one that's continuous on the rationals and discontinuous on the irrationals, because that's impossible and the proof for that is really complicated. But what about the opposite? Can you make it continuous on the irrationals but discontinuous on the rationals? Let's see if you can figure out a function that can do that. Thanks for watching. Like, comment, and subscribe, and I will see you all next month with whatever I decide to do. Peace.